In the last two videos, we talked about the theory of exact equations, how we could test if an equation is an exact equation, and how we could solve a differential equation that we know is exact. And we were pretty heavy on the theory when we were doing that. We said, okay, if you have some kind of function, some kind of differential equation that is in a differential form, which is to say that you have some function of x and y times dx plus some function of x and y times dy equals 0. It might be exact, we don't know. And the way that we test it's exact is that if the partial derivative of this first function with respect to y is equivalent to the partial derivative of the second function with respect to x, that tells us that there must be some greater function one level above them, such that the partial of that function, f of xy, with respect to x, is this first function. Partial of it with respect to y is the second function q, because of Clairaut's theorem, which states that mixed partial derivatives must be equal. If that's sounding pretty foreign or alien, maybe just go watch those videos. Hopefully it'll make more sense then. And so we know, okay, if the mixed partials are equal, there is a function, so that the partial with respect to x of it is that p of xy, and the partial with respect to y is q of xy. We don't know what that function is, but we can classify the differential equation now as exact. Once it is exact, we can use a fact. We know the total differential of f here is this, and we know that the total differential is really the same thing as the differential form of the differential equation. But if we know that that must equal 0, then df equals 0, which tells us that if once we find that encompassing function, whose partial derivative with respect to x is p of xy, partial derivative with respect to y is q of xy, once we find that f of xy, the solutions to the differential equations will just be that f of xy equals some constant c. Now, once we did that, we were able to figure out a method for actually solving for f of xy using this. Let's not worry about that for now. Let's actually delete all of this. Scary, right? Scroll back up and think about some example problems. So again, same textbook, section 2.4, steadily working through it. Let's do problem 1. So these first problems, we're going to be asked to classify the equation as separable, linear, exact, or none. So question 1 asks us to classify the differential equation x squared y plus x to the fourth times the cosine of x, and this is dx, minus x cubed dy equals 0. Alright, let's test if this is exact, because that's what we know how to do first off. So, if it was exact, then we would have that this is p of xy, this is, including the negative sign, q of xy, and if it was indeed exact, then we would have that the partial derivative of p with respect to y equaled the partial derivative of q with respect to x, so let's calculate that out. The partial derivative of the left-hand side here, the x squared y plus x to the fourth cosine of x, with respect to y, equals x squared, because this y here, this goes away. And this entire term is just in terms of x, so this is the partial derivative of p with respect to y equals x squared. Partial derivative of q with respect to x, well, we just have this negative x cubed term. That's going to turn into negative 3x squared, and we see these partial derivatives aren't equal. They're close to being equal, but one of them has a negative 3, and they have to be exactly equal for it to be exact. So, okay, is it exact? No. So it is not exact. Okay, let's think about what we might want to test next. Maybe we want to test if it is separable. Could it be a separable differential equation? Well, to test for separability, we would have to move move everything to the other side. So we have a derivative and then equal to some stuff. So let's check it out. Let's see if it is separable. So let's divide by dx so that we have x squared y plus x to the fourth cosine of x minus x cubed dy dx equals 0. And as we were doing before, we can kill two birds with one stone and put this on the other side of the equation, but with a minus sign. So let me go back to this. Let's do this with a minus sign. Minus. And then, of course, we also have a minus sign here, though, so we can make it a plus sign. And we can then divide by x cubed to get ourselves our final answer, which is that dy dx equals, if we divide by the x squared here, we're going to get y over x plus x cosine of x. And now we have to ask ourselves the question, now that it's in this form, is it separable? And unfortunately, it is not separable because of this addition. We have a y and an x added to an x, function of x. So this does not look to be separable, unfortunately. All right, well, our only last test is if it could possibly be linear. So now we're asking, is it a linear first-order differential equation? Well, in order to test that, we can just use this form that we have, subtract the y, and we'll get ourselves that y prime, which is this dy dx, y prime minus 1 over x times y, I'm moving the 1 over x there, out, equals x cosine x. All right, this is linear because we only have functions of x out of these y's, so we have found what this differential equation is. It is a linear differential equation. All right, let's remove this all and try another example. And I'm going to now actually intentionally pick one that is exact so that you get a good idea of what an exact equation test looks like. So, okay, let's do problem 4. So problem 4 asks us to classify the differential equation y e to the xy plus 2x dx plus x e to the xy minus 2y dy equals 0. And what you might notice right away is there's an odd sort of symmetry to this problem, right? And another thing you might notice is you might get tricked. If you tried to take the partial of this with respect to y, you'd get -2. Partial of this with respect to x, you get +2, and you wouldn't think it's exact. But let's do this correctly and say, all right, this here is what we've been calling p of xy. This here is what we've been calling q of xy. Let's go ahead and take the partial derivative of p with respect to y, and all right, what's this going to equal? This is going to be, all right, well, we have a y, function of y times another function, so we're going to use the product rule. So first, for this y e to the xy term, let's take the derivative with respect to y. So that's 1 times e to the xy, and then it didn't take the derivative of this e to the xy. Now in the second term from the product rule, we're going to not take the derivative of y, but do take the derivative of e to the xy, which is going to take down an x from the chain rule, and then of course e to the xy does still stay the same. And now the derivative of 2x with respect to y is 0, so we can leave it as that. All right, so let's draw ourselves a dotted line here, because now we're going to be calculating the partial derivative of q with respect to x. This is going to equal, again, we're going to have to use the product rule. So first, derivative of x is 1. We're just going to be left with e to the xy. And then we're going to add on partial derivative, derivative with respect to x of e to the xy, and then x is unchanged. So derivative with respect to x of e to the xy, the y comes down from the chain rule this time. Y e to the xy. Lo and behold, what we see now is that for this equation, we have that the partial of p with respect to y equals the partial of q with respect to x. Because these are equal, it implies that our equation is exact. So if you want some of your own practice, you can go ahead and solve this equation. I'm going to solve in a different exact equation in the next video. But if you want your own practice, you can try to solve this one on your own also. All right, I'll see you in the next video.